All right, so we need to do a new one for 10-7, so here we go. These two formulas right here that you see are really the same formula. It's just one of them is more for finance and one of them is for more growth and decay. All right, but really I look at them the same because if you look here on this side, there's a Y, and right there just happens to be an A. All they did was change the letter. Okay, but where that Y is and where that A is, both of them stand really for the same thing, and we will call it the end amount. That's what the Y and the A stand for. So however much of something you have at the end, maybe it's money, okay? Maybe it's an element. Okay? Could be grams, kilograms, dollars, who knows, okay? More like if it's dollars, we're going to use the one at the bottom. All right, this N in this top one and this P in the bottom one also stand for the same thing because you can see they follow the similar pattern, right? Right? So the N in the top one and the P in the bottom one stand for the start amount. So it could be money, grams, whatever. But whatever label you have for the start amount, your label for the end amount better be the same. You don't want to, start with grams and end up with dollars. Okay, that's probably not going to work out very well for you. Okay. Now, I'll be honest, in years past, I asked, well, what do you think E is? And people give me all these strange things of what E might stand for. E is not a variable in this particular situation. E is a number. And if you remember from when we did all the stuff earlier, E to the first power is about 2.71828 and keeps going on forever and ever, right? It's a number my calculator knows. So that E right there and that E right there is just a number. It's at 2.71828, blah, 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 blah. Okay? So you can imagine that the K up here and the R down here also stand for the same thing. Okay? And what those stand for is a rate of some kind. And the only note I can give you is use the decimal form. Okay. So if I ask you for K, just leave it as a decimal flat out. Down here, this one's more financial, right? So normally rates are given as percents. So down here, if I ask you for R, give it to me as a percent. If I ask you for K, give it to me just as a decimal. Okay? Yeah, the one at the bottom, R, always give it to me as a percent. But when you put it in the formula, use the decimal version when you put it in the formula. Okay? But if I ask you for it, give it to me as a percent. And T is probably only one that actually kind of makes sense here. T, in both formulas, at least it's the same. T stands for, time. The amount of time depends on what the problem tells you. It could be minutes, days, hours, years, centuries. It all depends on what the problem tells you. Okay? So in all honesty, I kind of think they're the same formula. Okay? Because look at the format. They're all the same, except for the R and the K is really about the only thing that makes a difference. Okay? So if you look at the growth and decay formula, K is going to be a big deciding factor. If K is positive, do you think it's growth or decay? If this K value right here is positive, do you think it's growth or decay? Growth. And if it's negative, it's decay. Very good. Okay. We really hope not to put a negative down for R. That means you're losing money. So we hope to avoid that at all costs. Okay. But this only works if it's compounded continuously at the bottom. Well, let's just jump in and see what we can do. For a radioactive element, I'm not going to tell you which one because I'm actually not so sure that this particular element exists. It says K is negative 0.377. So the fact that K is negative, it means we are growing or decaying? Decaying, definitely. When T is measured in days, see how it tells you? It tells you what it is. how long will it take 500 grams of this particular element to reduce down to 200 grams? Well, we're going to be using this version, not only because they told me K, right, but also because this is it's growth and decay. It's not financial. Okay, it's not money. It's rather interesting. In the past, some students have struggled to substitute information into the equation here. Y is supposed to be the end amount, correct? Well, what is the end amount in this problem? Very good. A lot of students want to say 500 because we're used to things getting bigger, right? But in the end, there's only 200, right? So very good. The end amount is actually 200. N is the beginning amount. Well, if 200 is what we ended up with, we must, 500's got to be the other one, right? E is just E, is a number. I happen to know K. And I'm going to put it in parentheses so that we can really distinguish the T there. And before we go too much further on this one, I want to point out something that some of you did wrong, the other day here in just a second. I'm taking a look, and I want to solve for T, not for E, right? E, we know what that is. I want to solve for T. T happens to be in the exponent, which means we will probably need logarithms of some kind. Okay? Many of you the other day just tried to put a logarithm right here. Okay? Unfortunately, this 500s to the first power, it's not all to that power. Okay, you got to be careful. Okay? So my suggestion here is let's not try and just sneak a logarithm here real quick. Let's get this term over here as much by itself as we can. Can I get it more by itself than it is currently? Yeah, what would we do? How could I get this variable more by itself, that T? Yeah, let's divide the 500 out of it. Because isn't that really how it's attached right here, by multiplication? So let's divide by 500. On this side, they just cancel. So over on that side, I'm left with e to the negative 0.377t. And what actually is on the left-hand side? We can save ourselves a lot of typing if we, yeah, it's 2/5, right? Because all that cancels, we're just left with 2/5. Now, the term that has the variable in the exponent is now actually by itself. So now we have to decide to take a logarithm. You can take any log base you want. Okay, for those listening to the recording, I am walking over by the calculator right now. On our calculator, we have common log and natural log. Those are the two most helpful. I think in this particular case, one of them is way more helpful than the other one. Any thoughts on which one, common log or natural log, might be more helpful? Why natural log? Why would that be more helpful? Yeah, it's base. Natural log really means log base e, right? I have an e in the problem. Very, very helpful to use natural log. So let's do that on both sides. Take the natural log over here, natural log over there. Notice, am I going to my calculator yet? I went to point at the calculator, but am I actually typing anything into a calculator yet? No. Let's get t as much by itself as we can and type into the calculator once, if we can, because then we don't have to round anything. So over here, I have the natural log of 2/5. What advantage do we have over here on the right-hand side then? What can I now do because there's a logarithm on this term? No, we're not going to divide it over yet. What does it allow me to do because there's a logarithm on it? This is, yep. But what can I do that's really important? I can take this exponent and move it out front. I think most of you already had that written down, which is why most of you are on the next step. All right? But we got to remember we're doing the recording, right? We got to help them out, right? So we can bring that out front. That's an E. Sorry about that. Looks like a C. Okay, so now I think I've caught up to where most of you were just a second ago. I think a lot of you brought it out front already. Now, somebody, I'm not trying, I'm going to try not to mention names. Somebody said, isn't the natural log of E just 1? It is, because it's saying log base e of e. E to what power gives you e? The first power. So this is just 1, so that's good. So think of where we've come from in this problem. We started way up here where the variable was nowhere near by itself. Look at where we are now. The variable is almost by itself. We're doing really good. So here's our variable right there. We got to get it by itself, so let's divide by. On this side it cancels, leaving me with my variable of t. Now that t's by itself, now go start typing into that calculator. Okay? So I'm going to wait till everybody has this written down so that I can go to the calculator and we can type it in to make sure you type it in properly. Okay? Closing off parentheses and negative signs and all of that could cause problems. All right, so here we go. I don't even know what I have on mine. Okay, nothing. So here we go. Natural log of 2. You just hit divide on these. Divide by 5. You have to close off this parenthesis that I just did. You have to close that off, okay? And we're going to divide it by, now it's this very bottom one. It's the opposite. We don't want to subtract, okay? The opposite of point, what is it, 377? I think, right? I could have put all the denominator in a parenthesis if I wanted to. I don't have to for this problem. Everybody ready? Here we go. So that's what I got. 2.4305 if you round it that far out, right? Is anybody unable to get that to come up on their calculator? Because let's make sure the calculators aren't the problem. Because some of them have weird settings. How come this is positive? Seems kind of weird. I'm dividing by a negative. How come it's positive? Uh-oh, making you think. Because my numerator, if I actually typed out just the numerator, is actually negative. It's e to what power would give you 2/5. 2/5 is less than 1, correct? So it must be a negative. It's a negative over a negative, which makes it positive. So what's our label on this? 2.4305. So t equals 2.4305. What's days, right? Well, I don't know about you, but I would strongly recommend you stay away from that element. You will get very sick very fast if you were anywhere near that element. That really means it takes 2.4 days for 2/5 of it, well, actually 3/5 of it to be gone. Because only 2/5 of it remains. That is very radioactive. Very sick, very fast. Any questions of any one step that we took there? No? Okay. Uh-oh, financial. Let's try this one. So if I invested $1,000 at 2% annual interest, that rate happens to be compounded continuously. What that means is once I compound it, it compounds again. And it compounds again. That means I keep getting interest over and over and over and over. But I'm only getting 2% for the whole year, so every time it compounds is really, really, really small. All right? And so then when will the investment double in value? It seems as though I have not given you enough information to fill out that. Seems I've left you kind of out there with not enough information. Well, this A right here is supposed to be how much I end up with, isn't it? Did I tell you that number? Not directly. But you can determine that number rather easily. 2,000, right? I want to double my money, right? If I started with 1,000, doubling it would be 2,000. So I want $2,000 when I'm done. P is what you started with, right? Would typically be called principal. That's what the P stands for. Not like Principal Nelson, but principal in starting amount, which would be, in this case, 1,000. E is just E. Be very careful with your rate, please. 2% means 2 out of 100, right? Or 2/100ths. So you have to write it in decimal form when you use it in a calculation. And so 2% as a decimal is, right? That's 2/100ths if you said it to somebody, right? So 0.02 and then t. Do you see how we once again have a variable in the exponent? So logarithms again, okay, everybody's favorite. But should I just put a logarithm right there, right now, in front of the 1,000? You know, a lot of you are shaking your head no, because it's got that 1,000. I got to get that 1,000 out of there. Okay. Luckily, that's pretty straightforward, just like we did before. Look at what magically happens on the left-hand side, though. I get a 2. And what did I want to do? I wanted to double my money. Look at that. Equals e to the 0.02 t. So I've isolated the term that has the variable in the exponent. So now take your logarithm. Any one you want. I think natural log is, once again, our best choice. Okay, so natural log of this side, natural log of that side. The reason is this can be brought out front. So it's the natural log of 2 equals 0.02 t times the natural log of e. On the last problem, we didn't really deal with natural log of e very much. That's because the natural log of e is 1. It's log base e of e. It's 1. And I think some of you are actually past me on this problem. So I better catch up. So we don't have the variable by itself yet. So let's divide by this 0.02. Okay. So it's the natural log of 2 over 0.02 will give me t. Let's go ahead and type that in. Has everybody written it down that needs it? Yeah, I hear somebody asking, like, what's the label on this one? That's a good question. We have to talk about that one. So natural log of 2, right, divided by 0.02. Now, I know you've probably already hit enter, but I have a positive on the bottom. Is my top positive or negative? Because it's saying e to what power would give you 2. It's greater than 1, so it's going to be a positive. Not a very big positive on top, but it is a positive. Okay, so it's positive over positive, so I'm going to expect a positive answer. Let's say for time, that's good, right? If we got a negative, we might start wondering what happened. Okay, so 34, let's just go to 34.7 for the purposes of what we're doing right now, okay? If you went further out, it's fine. Don't worry about it, okay? But now somebody asked that really good question, like, is it still days or is it something else now? I kind of very, in a sneaky way, put that information in the problem, what time was. Okay, I stuck it in there by saying annual, which means this would be given in years. Let's face it, we wish it was that many days. That would be awesome. 34 days, we doubled our money. Find that bank for me, right? We'd all be going there. But unfortunately, it's 34.7 years, all right? Unfortunately. And again, where I snuck that in there, whoa, was right there. Okay. Okay. Any questions so far? All right. What we're going to do now is we're actually going to come up with a formula. This formula is actually fairly commonly used. It is the decay formula for carbon-14. For those of you that maybe don't remember from chemistry or haven't had chemistry, carbon's atomic number is 12. The fact that it's carbon-14 means it's an isotope, okay? Because it's not matching the 12, right? And so this is actually the isotope they use to date fossils. It's called carbon dating, okay? It's saying that the half-life of carbon-14 is 5,760 years. Obviously, that's rounded. But what that means is if I started with a certain amount of carbon-14, 5,760 years from now, I would have half of that. So I'd have half of what I started with. And then another 5,760 years, I'd have half of what I had left over, and so forth and so on. You see how it would take a long time? Okay, and in fact, would it ever all be gone if I keep getting rid of just half of it? Half of what I have, it would never all be gone, right? Okay, just like if I kept getting halfway to that wall, I'd never actually get to that wall. Right? So what we're going to try and do is we're going to try and figure out what can I put right here so that I could figure out the formula for carbon-14. What can I put in there for K so that if I gave you how much carbon was left in something, you could tell me how old it was. Okay? So we got to go figure out basically K. All right. Well, let's figure out over here. I'm just going to write it all. So our goal is to eventually figure out K and put it over there in that blank space that I have in blue. Well, uh-oh. Well, we know the time. Time is 5,760, right? I don't know K. Okay, we don't, well, E's a number. I don't know K, but I do know this is that. So what do I put for N and K? It appears as though I have left you with no information again. Think of what half-life means again. Half of it will be gone. Kevin? Okay, it was said that, I said somebody's name, I apologize for that. Any number where y is half of n, I know which two numbers I would choose. 1 and 2, yeah. Or some people in the other hour said 1 and 0.5. I'm like, well, you could do that, and that would be one way of doing it. So now we got to figure out 1 and 2 are really good numbers, so the 2 would go here, right? And if I have half of it, there would be 1 left over there. So could you have literally taken like 2 million and 1 million? It still would work out the same, because what's our very next step going to be every time is to divide by the 2. So what's going to be sitting over here is the half we're talking about anyways, right? So it doesn't even matter. All right, so let's divide by the 2. There's that half. Right? It didn't even matter. Okay, so half equals, are you okay if I put 5,760K? Or is that going to mess with anybody if I switch those around? It doesn't really matter. I'm just going to, it's a personal preference. Oh, there we go again, variable in the exponent. Hey, but we've isolated the term that has the variable in the exponent, so we're doing awesome. Once again, any logarithm will work. Our calculator has 2 of them. Well, why don't we go with natural log? That seems like a best choice. Because we have a base e. Again, then this can go out front. So it's natural log of a half. And I'm sure you're all very clever. You're starting to pick up on this process rather quickly. Okay. This here is 1. So to solve, I just have to divide by. Now, here's the interesting part, though. Your calculators are going to give you this information in a variety of ways. Some of your calculators are just going to give you the decimal. Some of your calculators, those that might have some more like mine, is going to give it to you in scientific notation. Okay. So I'm going to take this. Everybody got it written down so I can go to the calculator here? Everybody ready? All right, let's find out what mine's going to do. Well, let's get rid of this. So natural log of 0.5 divided by 5,760. Okay, I know this answer is going to be negative for a variety of reasons. It's decay for one reason. Another reason is natural log of 0.5. 0.5 is less than 1, right? So it's going to be a negative over positive. This is going to be a negative. Okay. Now I know, well, 99% sure mine's going to give it to me in scientific notation. Some of your calculators might just give you the decimal. Okay. I know this is scientific notation because this right here is how these calculators give scientific notation. It's not a lowercase e, is it? It's an uppercase. Now, did most of yours just give you the decimal? Does anybody have like an 83 or an 84 they were using? No? So if you do, here's how that would work. Okay? What this means is times 10 to the negative 4th, which basically means go that way 4 times with your decimal, correct? So here we go. There's the decimal. This negative would be out front. Is that the decimal you got? Negative 0.00012. Okay? So keep in mind that that's how that would work for you. So it's negative 0.00012. So if I were you, I would go back up here to what we wrote earlier. And what can I put in that little blank right now? I can put that right there. This right here is a very simplified version of the carbon-14 formula. So now I could tell you how much of carbon I had left, and you should be able to tell me how old it is by using that formula I just put a box around. Any questions where the information came from? Okay. Well, let's go try and find out how old something is then. How old is a fossil if it has 1/5 of its carbon-14 remaining? Well, good thing we just learned the formula. Now, this formula only works for carbon-14. Don't try this for other isotopes. Okay? So 1/5 of it remaining. We could make a guess. Because if a half-life's 5,760, to do that twice would get me into about 11,000 range, right? Which would be a quarter, though. A half and a half would be a quarter, right? We have 1/5. Well, obviously I'm asking you to find t, so I better be able to fill out y and n, which we can. We can fill out y and n. There are lots of options. To go with what somebody said earlier, just as long as y is 1/5 of n, we're good. So somebody in the other R said 1 and 0.2. Like, well, I don't know if that's our best choice. How about 1 and 5? Right? So if I started with 5, I would end up with 1. That's 1/5 of 5. E to the negative 0.00012 t. Okay? So what I'm going to do is I'm going to pause the recording, and I would like you to take a shot at solving that one on your own. So those listening to the recording, please also try. Don't just continue with the recording. All right, so hopefully you had enough time to try that one. If not, make sure you actually pause the recording. So if we follow the same process we've been doing, pretty much because we have a variable in that exponent, let's isolate that term, right? So it'll be 1/5, surprise, surprise, equals e to the negative 0.00012 t. And we got to get that variable out of that exponent if we're going to try and solve. I don't think we're going to get the bases the same, so let's take natural log of both sides. All right, so it's natural log of 1/5 equals negative 0.00012 t times natural log. Woof, that says he, not natural log. That is 1 divided by negative 0.00012. Oop, negative. Don't forget that, otherwise your answer is not going to make sense. But again, our numerator is going to be negative. Over negative, we will get a positive. A good thing. We're solving for time, right? All right, let's find out what we get. Whoops. I want to get rid of this. That might be really distracting. All right, so natural log 1/5. Whoops. And we are dividing by, do use this little button down here at the bottom. You just saw light up in red. So $13,411, not dollars, 411.9826 what? Years. Yeah, how do we know it's years? Couldn't it have been minutes? Very good. The half-life is 5,760 years. So that's how we determined K was based off of Years, excellent. That's why we know this is years. So really not all that old compared to other things. Unfortunately, ours, all this stuff's rounded, so the further stuff went back, the further they figured they're maybe off by 2 million years on some of their fossils because of all the rounding. The further you go out, the worse the rounding gets, right? All right. What I would like you to do for tomorrow is try to solve example 5. Okay? So if you're listening to the recording, you'll have to stop in and check with me on the answer to example 5, or check with classmates.